Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. A support engineer just spent 20 minutes digging through the knowledge base for a fix that's definitely there. They typed transaction failure. The doc that solves it is titled Payment Gateway Timeout. Not the same words, even though they mean the same problem. This is what a vector database fixes. It finds things by meaning, not by matching characters. By the end of this video, you'll do 3 things cold. Define a vector database in plain language, no buzzwords. Explain how approximate nearest neighbor indexing makes similarity search fast instead of grinding through millions of points. And build a working retrieval pipeline with real code you can run yourself. A vector database stores high-dimensional vectors, arrays of floating point numbers, and lets you search for similar items using approximate nearest neighbor algorithms. Not exact keyword matching. A traditional database looks for where status equals open. A vector database asks, what's nearby in meaning? That's the shift. Picture a 2D grid. One axis is size, the other is color. A cat lands at small and black. A horse lands at medium and brown. Now drop in a query for medium brown animal. The horse is right there. The cat isn't. That's how vector proximity captures meaning, even when the word horse never appears. Quick checkpoint. Without naming the technology, what's the one job a vector database exists to do? It finds things that are semantically similar to your query, not just character for character matches. If you answered that, you've already got the foundation. Before we continue, let's quickly connect this lesson to the previous one. Every document, image, or piece of text first passes through an embedding model that converts it into a dense numerical vector representing its semantic meaning. Those vectors become the records stored inside a vector database. When a user asks a question, the same embedding model converts that query into another vector. Instead of searching for matching words, the vector database searches for nearby vectors that represent similar meaning. Embeddings give the data meaning. The vector database makes searching those meanings fast, scalable, and practical for real-world AI applications. 2 common ways to measure closeness. Cosine similarity looks at the angle between vectors. It ignores how long they are, so a short document and a long one can rank side by side if they're about the same thing. Euclidean distance measures the raw straight-line gap. Both are widely used. The right choice depends on your data and embedding model. HNSW, Hierarchical Navigable Small World, builds a multi-layer graph. The top layer is sparse with long-range edges that jump across the space. Each layer below gets denser, refining the neighborhood. A query starts at the top, takes a few big leaps, then drills down to the exact closest points. It's like zooming in on a map, trading a little accuracy for dramatically faster search compared to scanning every vector. Checkpoint. Why settle for approximate instead of exact? Because scanning every single vector in a high-dimensional space is painfully slow at scale. Approximate nearest neighbor algorithms give you results that are almost as good in milliseconds instead of seconds. For semantic search, That trade-off is a no-brainer. Finding similar information among millions, or even billions, of vectors requires more than simply comparing every record one by one. Modern vector databases combine several indexing techniques to make retrieval both fast and scalable. Some methods organize vectors into neighborhoods so the search can quickly navigate toward the most promising results. Others group similar vectors together or compress them so much larger datasets fit efficiently into memory. The important idea isn't memorizing every algorithm. It's understanding that these indexing strategies dramatically reduce the amount of work required to answer each query. As your datasets grow, these optimizations become the difference between waiting several seconds and getting relevant results almost instantly. We'll explore these indexing techniques in much greater depth in a future advanced lesson. Time for a quick recall check. Which algorithm builds a multi-layer graph to speed up approximate nearest neighbor search? It's HNSW. HNSW creates a layered graph that lets a query jump across the space and then drill down to the exact neighbors. IVF works by clustering vectors and searching only nearby clusters. And product quantization compresses vectors to save memory. 3 distinct tools for different challenges. Let's step back and see the big split. A traditional database like PostgreSQL or MySQL stores rows and columns. You ask, give me the transaction with ID 40231, and it does an exact match. That's perfect for banking ledgers. A vector database, on the other hand, stores embeddings, dense numerical vectors. You ask, show me couches that look like this photo, and it computes similarity across millions of items. It's the difference between a filing cabinet and a search engine that understands meaning. Vector databases are also the engine behind RAG, Retrieval Augmented Generation, where you pull relevant document from a vector store and feed them into an LLM's prompt to ground its answers. That's a pattern we'll dive deeper into soon. Vector databases aren't just for chatbots. Here are 5 real-world places they shine. 1. RAG, where a support bot leverages your whole knowledge base. 2. Semantic product search. Shoppers find items by vibe, not exact keyword. 3. Content recommendation, matching on the meaning of a movie, not just genre tags. 4. Anomaly detection, spotting network intrusions as far from normal patterns. And 5. Facial recognition, comparing face embeddings in milliseconds. In each case, what you're really doing is asking, what's similar to this? And that's exactly what a vector database was built for. Quick check. Name a use case where a traditional database would fail. The answer is any semantic search, like photo-to-product matching or show me movies similar in mood. A traditional DB could at best look for exact tags. A vector database understands the vibe. That's the fundamental shift. And this is the main event. A user types a query. The same embedding model that built your document vectors now turns that query into a vector. That query vector hits the vector database, which retrieves the top K most similar chunks. Those chunks get stuffed into the LLM's context window, right next to the original prompt. The LLM then synthesizes an answer grounded in that retrieved knowledge. This is RAG in one flow, and the vector database is the middle that makes it fast and relevant. As we covered in Part 1 and 2, retrieval quality is everything, and the Vector DB is the engine that drives it. Here's where most people get it dangerously wrong. A junior dev at a legal tech startup just deployed a RAG chatbot. The system returns accurate, well-written summaries, but it completely misses the exact case number the lawyer typed in. Why? Because they threw out full-text search and relied only on vector retrieval. Real-world search isn't just about meaning. You need to match case 2024-789 exactly, while also understanding that the surrounding paragraphs are about intellectual property. Pure vector search can drift away from exact terms. The fix is hybrid search. BM25, a proven algorithm for weighting exact keyword matches, for precision on keywords, vector similarity for semantic breadth, and a fusion algorithm to merge the results. Azure AI Search and many other platforms do this natively. If you ignore this, your RAG accuracy tanks on queries with specific identifiers. And when we get into FAISS, Facebook AI Similarity Search, pronounced FAISS, in the next scene, you'll see how these indexes can bring it all together. Remember, your vector database is a piece of the puzzle, not the whole picture. Let's get hands-on with FAISS, a library for efficient similarity search and clustering. In just a few lines of Python, you can build an index, add vectors, and search. We create a flat L2 distance index. Flat means exact search, comparing the query to every single vector. We generate random data to simulate real embeddings, add it, and then search for the top 5 nearest neighbors. This demonstrates the core search loop. For larger datasets, you'd switch to an approximate index, but this snippet gives you a working vector search engine quickly. If managing your own vector database sounds like overhead, the major clouds have you covered. AWS OpenSearch offers KNN search capabilities, often used to blend vector and traditional queries. Azure AI Search combines vector, keyword, and semantic ranking, and on Google Cloud, vector search is built right into BigQuery and Alloy DB, as confirmed by the official docs. Always check the latest documentation for up-to-date features, but each of these abstracts away the tricky indexing work so you can focus on your use case. If you want full control, the open-source world is thriving. Milvus handles large-scale vector data across distributed clusters. Weaviate provides a GraphQL interface and integrates with various embedding services. Chroma offers a straightforward Python API, making it popular for quick RAG experiments. And QDurant, built in Rust, emphasizes raw speed and memory efficiency. Each tool has its own trade-offs, but they all tackle the same core problem: fast similarity search on vectors. Check their official docs for the latest features. One more quick recall. Which open-source tool is noted for its simple Python API for vector search? It's Chroma. Chroma is lightweight and often used in RAG prototypes because you can stand up a collection with very little code. Imagine you upgrade from 768 dimensional embeddings to 30 72-dimensional ones. In that ultra-high dimensional space, the curse of dimensionality can make all points appear roughly the same distance apart. That kills similarity search because there's no clear nearest neighbor. High dimensions aren't always better. They need normalization, appropriate indexing, and sometimes even dimensionality reduction to stay useful. Always benchmark your recall when you change embedding models. Imagine an IT administrator searching for KB47291 password reset. They need the exact knowledge base article associated with that identifier, but they also want troubleshooting guides describing similar password reset issues. Hybrid search sends the same query to 2 search systems at the same time. A traditional keyword index retrieves the exact knowledge base article, while the vector index retrieves semantically related documentation. A ranking algorithm then combines both result sets into a single ordered list. The result is precise matching for identifiers together with intelligent semantic search for related content. That's why hybrid search has become the preferred architecture for many enterprise AI search applications. Quick recall check. What problem does hybrid search solve that pure vector search doesn't? Here's Chroma in raw Python, start to finish. We spin up a client, create a collection, and bind a sentence transformer model that outputs compact 384-dimensional embeddings. Perfect for small projects. We add 2 documents with metadata, one about server restarts, one about a memory leak patch. The add method automatically generates embeddings, indexes them, and stores everything in one call. When we query for memory leak fix, Chroma returns the patch document as the top result, even though the word fix never appeared in the original text. Add metadata fields like date and topic, and you can filter by exact values before or after the semantic search. Now let's look at what using a managed vector database feels like. First, create a new index and configure it to match the dimensions produced by your embedding model. Next, choose an appropriate similarity metric, such as cosine similarity, and provision the index. Once it's ready, upload your vectors together with useful metadata like document IDs, departments, product names, or creation dates. When a user submits a natural language query, Pinecone compares the query embedding against the indexed vectors and returns the closest semantic matches in milliseconds. The exact interface and available features will continue to evolve, but the overall workflow remains the same. Generate embeddings, index them efficiently, attach meaningful metadata, and retrieve the most relevant results with minimal operational overhead. The fundamental trade-off in vector search is latency versus recall. Approximate algorithms like HNSW and IVF sacrifice a tiny fraction of recall for dramatically faster queries, making real-time RAG possible. The right balance depends on your use case. Always benchmark with your own data. Sites like anbenchmarks.com show community comparisons. Quantization deep dive. One final checkpoint before we move on. As vector databases grow from thousands to millions, or even billions, of records, what's one technique engineers use to reduce memory usage while keeping search fast? The answer is vector compression. Instead of storing every vector at full precision, the database stores a much smaller representation that still preserves enough information for efficient similarity search. Different databases use different compression techniques behind the scenes, but the goal is always the same: reduce memory requirements while maintaining useful retrieval accuracy. The important takeaway isn't memorizing individual algorithms, it's understanding why compression matters. It allows AI systems to search massive collections efficiently without requiring enormous amounts of memory. As teams move from proof-of-concept projects into production, the same mistakes appear again and again. First, creating an index with dimensions that don't match the embedding model, causing every query to fail before retrieval even begins. Second, ignoring metadata filtering, forcing every search to scan documents that could have been narrowed by department, customer, language, product, or date. Third, relying only on vector similarity when hybrid search would better handle exact identifiers like ticket numbers, case IDs, or product codes. Fourth, tuning only for maximum recall while ignoring latency, making the application too slow for real-time use. Finally, generating poor quality embeddings or using different embedding models for indexing and querying, which dramatically reduces retrieval accuracy. A vector database can only retrieve information as effectively as the embeddings stored inside it. Avoid these common mistakes, and your retrieval pipeline will be far more reliable, scalable, and accurate. Let's test your understanding with a real production scenario. Your vector database is running successfully, but users complain that search results are consistently irrelevant. What's one of the first things you should investigate? Verify that you're using the same embedding model for both indexing and querying. Confirm the vector dimensions match your index configuration, and check whether metadata filters are unintentionally excluding relevant documents. These are among the most common causes of poor retrieval quality in production systems. Finding the right answer isn't just about choosing a vector database. It's about making sure every part of the retrieval pipeline works together correctly. Building a fast vector database is only part of the challenge. It also needs to retrieve the right information consistently. Exact search delivers the highest possible recall, but as datasets grow, the computational cost increases dramatically. Approximate nearest neighbor algorithms make real-time semantic search practical by accepting a very small reduction in recall in exchange for significantly faster retrieval and higher throughput. Choosing the right configuration is always a balancing act. Every production system must weigh recall, latency, throughput, memory usage, storage cost, and operational complexity. Improving one metric often affects another. Rather than relying solely on generic benchmarks, successful AI teams evaluate different indexing strategies using their own documents, workloads, and business requirements to determine which configuration delivers the best overall results. Let's lock in the 3 things you can now do cold. First, define a vector database. It's a specialized database that stores high-dimensional vectors and retrieves similar items using approximate nearest neighbor algorithms, not keyword matching. Second, explain how ANN indexing makes similarity search fast at scale by trading a small amount of recall for huge speed gains. Third, build a working retrieval pipeline. You saw Chroma in Python, Pinecone's managed console, and you understand how RAG ties it all together. That's the entire playbook. Go build something. Before we wrap up, answer one final question. Why do production AI systems rely on approximate nearest neighbor search instead of exact search? Because searching every vector becomes too computationally expensive as datasets grow. Approximate search dramatically reduces retrieval time while maintaining the level of accuracy required for most real-world AI applications. Understanding that trade-off is one of the most important concepts behind modern vector databases. You've now learned how embeddings become vectors, how vector databases organize and search those vectors efficiently, and why they play such a critical role in retrieval-augmented generation systems. In the next lesson, we'll build on everything you've learned by exploring chunking, one of the biggest factors affecting retrieval quality. You'll see how the way documents are divided can significantly improve or reduce search accuracy. If you're enjoying this series and want to continue building production-ready AI engineering skills, subscribe so you don't miss the next lesson. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson. Build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.